Okay, so let's start. So today we'll solve the assignment 12 for the course Linear Algebra NOC 23 MA 03. This is the last assignment for the course of this course. Okay, what is the first question? Let T1 and T2 be the two non-zero self-adjoint. So okay, just 1 minute, let me start the script. Okay, so T1 and T2 be two non-zero self-adjoint linear operator on a finite dimensional complex inner product space V, such that they will commute T1 T2 equals to T2 T1. Then which of the following statements are true? So two self-adjoint operators are given. So what is meant by self-adjoint? So this is the what is the first option is saying saying that T1 plus alpha T2 is self-adjoint linear operator for any alpha in C. Means by a complex number, it is saying that if T1 and T2 are self-adjoint operator, then T1 plus alpha T2 will be self-adjoint for alpha in C. So let's check that this is true or false. So option number 1, T1 is self-adjoint, means T1 star equals to T1, and T2 is also self-adjoint, means T2 star is T2. So we have to check for T1 plus alpha T2, T for alpha in C. T1 plus alpha T2 and take the adjoint. So by the properties of adjoint, it will be T1 star plus alpha bar T2 star, right? So we want this to be T1 plus T2 star, right? So we have to check that when this will be T1 plus T2 star. So if alpha is complex number, then it is alpha and alpha are not equal, right? So this is not equal in general, right? So this is not equals to T1 plus so first one it will be T1 plus alpha bar T2 because they are self-adjoint, but this may not be equals to T1 plus alpha T2 if alpha is purely imaginary. If this is real, then it will happen. Not true if alpha is purely complex number, means there is the imaginary part. So this is not in general true, means this is not self-adjoint. So T1 plus alpha T2 may not be self-adjoint. So first option is false. Now it is not. Next option is saying that T1 plus alpha T2 is self-adjoint linear operator if and only if alpha is real number. So let's check this. So from the first one we have seen that if alpha is real number, so let's say if, so converse direction, let's first do it. If alpha is real number, alpha belongs to R, then what will be the T1 plus alpha T2 star? It will be T1 star plus alpha, because this is real number, alpha T2 star and this is same as T1 plus alpha T2. So this is self-adjoint, which implies T1 plus alpha T2 is self-adjoint. And in the converse direction we have seen earlier. So we have to show that if T1, so let's assume let T1 plus alpha T2 is self-adjoint. and what we have to show that alpha is real number. To show alpha is real number, right? So we have seen earlier that as from option 1, let me write it here. We get T1 plus alpha T2 whole star. So this should be, so what we have got, this is T1 plus alpha bar T2. And as this is self adjoint given, as T1 plus alpha T2 is self adjoint, so this will give then T1 plus alpha T2 star will be T1 plus alpha T2. So this is called 1 and this is 2. So from 1 and 2, alpha equals to alpha star. From 1 and 2, alpha equals to alpha bar, means alpha is real number. So option 2 is correct. Now what is the next option? It is saying that T1 plus alpha T2 is normal linear operator for any alpha belongs to C. So when this will be normal, it is saying that for all alpha belongs to C, it is normal or not. Let's check. So what is meant by the normal linear operator? So T1 plus alpha T2, this A transpose, right? We have to check A transpose equals to A transpose A for to be normal. So this we have to check this to be equals to T1 plus alpha T2 star should be equal to T1 plus alpha T2 star. So this is true or not, we have to check. T1 plus alpha T2, this you have to check this, right? So first start with left hand side. Left hand side is T1 plus alpha T2 into, and note that the commutative property is given, right? So T1 plus T2 star, so this will be T1 plus alpha T2 and conjugate of this will be T1 star plus alpha bar T2 star, and they are self adjoint operator. So T1 plus alpha T2 into it will be T1 plus alpha bar T2, as T1 and T2 are self adjoint. Right, and next now use the composition rule. So what you will get, T1 square plus alpha bar T1 T2 plus alpha T2 T1 plus alpha bar T2 square, right? And now use that T1 commutes with T2, so which means T1 square plus alpha bar, it will be T2 T1 plus alpha T1 T2 plus alpha bar T2 square, because they commute, right? As T1 T2 equals to T2 T1. So this we got from the left hand side. Now calculate the right hand side. So RHS T1 plus alpha T2 star into T1 plus alpha T2. So this again use the definition T1 star plus alpha bar T2 star, T1 plus alpha T2. You can use that their self adjoint means T1 plus alpha T2. This I am not writing, you just you can understand T1 plus alpha T2 because they are self adjoint. And now if you apply the composition, it will be T1 square plus alpha T1 T2 plus, so this will be alpha bar, right? Alpha bar T2 T1 plus alpha bar T2 square, right? Now check, so suppose this I am calling it to be 1 and this is 2. So you can see that 1 and 2 are same, right? So from 1 and 2, from 1 and 2 we get T1 plus alpha T2 into T1 plus alpha T2 star equals to T1 plus alpha T2 star into T1 plus alpha T2. Means this is normal. T1 plus alpha T2 is normal for all alpha belongs to C, right? So option number 3 is correct. Now what is option number 4? It's saying that Pt1 is self-adjoint linear operator for any p belongs to complex polynomial, right? So let's see. So Pt1 it's a operator. It's saying that this is self-adjoint for any p in complex polynomial. So this is option number 4. So this is not true, right? So this you can check by just trivial polynomial. So take this polynomial. P of x equals to some alpha times x, right? Alpha times x, where alpha is complex number, because this is a complex polynomial. So you can take, then alpha belongs to, then p belongs to c of x, right? Then what will be the p of t1? P of t1 will be alpha t1, right? But is this self adjoint? So this is not, right, because alpha is complex number. So what will be the pt1 of star? So this is alpha t1 star, means alpha bar t1 star. T1 star is self adjoint, so it is alpha bar t1. So this is not equals to alpha t1 bar, right? So the pt1 is not self adjoint. So option number 4 is false. Now it's like this as earlier. Is it normal? Pt1 is normal linear operator for p is complex polynomial. So this will be true. Let's check this. Option number 5. So what will be the, so we have to check that pt1 is normal linear operator. For p belongs to c of x, right? So what we have to check that pt1 into pt1 star equals to pt1 star pt1 to solve, right? So how the polynomial, suppose let's take this polynomial, let p of x equals to a naught plus a1 x plus dot 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 an x to the power n, where a1 a2 dot dot an are complex number, right? Then pt1, how it is defined? It is defined a naught times identity plus a1 times t1 plus dot 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 an t1 to the power n, right? So this is the operator pt1. Then what will be the conjugate transpose adjoint pt1 star? So it will be the a naught bar I, right, plus a1 bar t1 star plus dot 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 an bar t1 to the power n whole star, right? So as t1 is self adjoint, so what you will get? So it will be a naught I plus a1 bar t1 plus dot dot dot, and t1 are commutes, so it will be an bar, it is t1 to the power n. So this is the adjoint, right? So this is the basically polynomial, it's p bar times t, p bar of t, right, t1. So what will be then this? Then pt1 into pt1 star, so it will be pt1 into pt1, this will be bar, and p and p bar as t1s are commute, right? So it will, so polynomial this, so this is same as p1 bar t1 pt1, right? So just multiply these two polynomial p and p bar, so you can see that as t1s, so they are commute, right, as t1 commute, so this will be the same as t1 commute with itself. So this is the same as pt1 star pt1, right? So therefore pt1 is normal for any p. So option number 5 is true. Now what is the next option? T1 T2 is normal linear operator. So let's check T1 T2 is normal linear operator or not. So this is option number 6. T1 T2 times T1 T2 star, right? So what it will be? T1 T2, it will be T2 star T1 star, and because they are self adjoint, so it will be T1 T2 T1, right, as T1 equals to T1 star, T2 equals to T2 star. So it implies T1, sorry, this would be T2, right? So this will be, this you can write T1 T2. Now this will commute because T2 T1 commute, so T2 T1, and this will be T2 T1, right, as T1 T2 equals to T2 T1. So this is same as T2 star T1 star, and this will be the T1 T2, right, because they are commute also. So let me write it here also, T1 T2, and then it will be T1 T2. So this is the T1 T2 star, and this is T1 T2. So they are normal, right? T1 T2 is a normal linear operator. So So option number 6 is correct. Now what is our next option? It's saying that q of, this is a polynomial in two variable, q of t1 t2 is normal linear operator for any real polynomial of two variable. So let's check option number 7. So q is a polynomial in two variable r of xy. Then we have to check that q t1 t2 is normal. So we have as early, because t1 and t2 commute, so what will be that t1 t2 star. So let's first check, take the polynomial, suppose qx, this we take, suppose a0 plus a1 x plus a2y plus a3xy plus dot 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 a sum k x to the power l y to the power m. Suppose this is a polynomial in two variable, so xy. Then what will be q of t1 t2? It will be a0 identity plus a1, sorry, it will be a1 t1 plus a2 t2 plus a3 t1 t2 plus dot 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 ak t1 to the power l t2 to the power m, right? Now take the adjoint, then what will happen? So q t1, so this is the linear operator, we will take the adjoint. So you have to take the adjoint of whole thing. So then it will be, and these are complex real number, a0 dot dot ak, they are real number. So it will be a0 I plus a1 t1 star plus a2 t2 star plus a3 t2 star t1 star plus dot 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 ak t2 m whole star t1 l whole star, right? Now because they are self adjoint, so it will be a0 I plus a1 t1 plus a2 t2 plus a3 t2 t1 plus dot 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 ak t2m t1 l, right? And now they commute, so they commute, then it will be same, you get a0 I plus a1 t1 plus a2 t2 plus a3, it will be again t1 t2, and using commutativity what you will get, ak t1 to the power l t2 to the power m, as they commute t1 t2 equals to t2 t1, right? So we get basically they are same polynomial, q of t1 t2. So then what will happen? Q t1 t2 star into q t1 t2 star, it will be basically these two are same, t1 t2, this is square, so this you can write q1 t1 t2 star q1 t1 t2. Yes, this is a normal, right? So q t1 t2 is a normal linear operator. So option number 7 is correct. So first question is done. Let's move to the question number 2. Okay, it's saying that let T be a linear operator on a finite dimensional inner product space B, then which of the following statements are true? If A is a square matrix with complex entries such that A square is normal, then so is E. So it's saying that if A square is a normal matrix, then A will be normal. So let's check that this is not true. First one. So let's take this example. A equals to 0, 1, 0, 0. So is this normal matrix? So let's check what will be the A star. A star will be 0, 0, 1, 0, right? Then what will be A star? A star will be 1, 0, 0, 0. And what will be A star A? 0, 0, 0, 1. So they are not same. So A star is not equals to A star A, right? Means A is not normal. So A is not normal. What will be A square? A square will be 0, 1, 0, 0, 0, 1, 0, 0. So this is 0, this is 0, 0, 0. So this is a 0 matrix which is normal, right? A square is a normal matrix. Trivially, A square is normal. So we have seen that A square is normal, but A is not normal. So the first option is not true. So this is false. So we get an example where A square is normal, but A is not normal, right? What is the next option? A matrix A is self-adjoint if and only if the corresponding linear transformation ALA is self-adjoint, right? So let's check option number 2. Given that A is self-adjoint, no, so A is self-adjoint and we have to prove that. So what is LA? Let's first LA. So this is a linear operator. How this is defined? It is A times X, right? So what will be the adjoint of this? So let's compute LA star XY, right? So this will be X times LA X with LAY, and LA is A times X, X A Y. So Y adjoint, it will be A star X Y, right? So this is true for all XY. Means what you get, LA star is, it is the adjoint of A, right? So then what will happen if, so therefore A is self-adjoint if and only LA star is, LA is self-adjoint, right? A is self-adjoint because if this is A star equals to A, then LA star will be LA, right? So therefore A is self-adjoint if and only LA is self-adjoint. So option number 2 is true. Now what is option number 3? The operator T is normal if and only if norm TV is equals to norm B. So this is called the isometry. if norm t v equals to norm v for all v, then it's called that the operator t is isometric. So it's saying that a operator is normal if and only if it's isometric. So this is not true. So let's solve this. Option number 3. So what is the question? T is normal if and only T is normal if and only norm Tb equals to norm V or all V belongs to vector space, right? So let's so that this is not true. So take a example. Take the corresponding matrix of the linear operator A. Let A be the corresponding matrix. So it is of the form 2 minus 3 3 2. So then and apply with this. So okay, then check that A is a normal operator. So this is easy, just compute A star and A star A. So they will be same. Check A is normal operator, normal matrix. Right. Then what will be the take V to be 1 1. Take this vector and apply it to A. So what will be A dot B? So it will be 2 minus 3 3 2 times 1 1. So then what we will get? So you will get minus 1 and you will get 5. So then what will be the norm of this vector? So norm of AB will be square root of 1 plus 5 square. So this is square root of 26. And what is the norm of B? Norm of B is 1 plus 1. So it is square root 2. So they are not same. So we have seen that A is a normal matrix, but this is not isometric. So AB is not equals to norm. So this is false. Option number 3 is false. Now what is option number 4? It's saying that every self-adjoint matrix A is symmetric, right? So is this true? Every self-adjoint matrix A is symmetric. Okay. What is self-adjoint? Let A is self-adjoint then. So self-adjoint means A is self-adjoint means A equals to A star. It's conjugate transpose, right? A is self-adjoint means A equals to A conjugate transpose, and A is symmetric means A is symmetric means A equals to A transpose. So this is the conjugate transpose means take the conjugate and transpose. So if A is a complex matrix, then this will not be true, right? So therefore this is not true. So let's take a complex matrix. A equals to 0 I minus I 0. Then what will be A conjugate A transpose? A transpose will be 0 I minus I 0. But what will be A star? A star will be, so now you have to take the conjugate 0 minus I 0. So therefore A equals to A, so it is self-adjoint but not symmetric, right? So therefore A is self-adjoint but may not be symmetric. may not be symmetric. So the option number 4 is false. Now what is the next? Every self-adjoint real matrix is symmetric, right? So this is true, as we have seen right now, because their conjugate transpose is same as transpose. So this is option number 5. So what we have to say, so given, what is given? A equals to A conjugate transpose and A is real matrix. Then what is, so A conjugate transpose, it's A bar transpose, so this is same as A transpose, so this is, and this is A, right? So we get A equals to A transpose, so which implies A is symmetric. So therefore option number 5 is correct. So question number 2 is done. Let's move to the question number 3. Okay. It is saying that let T be a linear operator on a finite dimensional inner product space V, and Tv equals to lambda times V for some V is non-zero V, and T star denote the adjoint of T. Then it is saying that if T is a self-adjoint, then the trace of the corresponding matrix is real for any basis B, beta of B, right? So it's saying that if T is a self-adjoint operator, then the trace of the corresponding matrix will be real. So this is the first option. So given that T is self-adjoint, given T is self-adjoint, so it is done in the class that every self-adjoint matrix is diagonalizable, right? So T is diagonalizable. So means, which implies, so there exists a unitary matrix or some matrix, invertible matrix you can say, U, such that T you can write T equals to U, means there exists a orthonormal basis, right, in which T can be write as diagonal matrix. So so that orthogonal basis, if you write it in matrix form, this will be called U. So then T can be written as U D U inverse, right, where D is a diagonal matrix, where D is a diagonal matrix. Right. So then what will be trace of T? Then trace of T will be then trace of U D U inverse, right? And you can check the trace of this is U D U inverse, trace is same as trace of D. This you can check this one, right? And what is the diagonal matrix? And you also know that as T is self-adjoint, so and in the diagonal it will be all the eigenvalues are there, right? So let me write a note here. As T is diagonal at self-adjoint, so all the eigenvalues are real. And D consists of the eigenvalues, right? So let's say lambda 1 up to lambda k. lambda n up to dot dot lambda n, these are all real number. Then d will be look like lambda 1 dot 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 lambda n and all other are 0. So then what is trace of d? Trace of d will be sum of these diagonal entries, summation lambda I, right? I equals to 1 to n, and as lambda is a real, so this is real number, right? So therefore trace of a is real. Therefore trace of a belongs to real number. So for self adjoint matrix, trace of t will be, and this is so this is does not depend on the basis, right? So for self adjoint operator, trace is real number. Now what is the next option? It is saying that, so suppose t is an eigenvalue of lambda is an eigenvalue of t, then it is saying that lambda bar is an eigenvalue of t star. Okay, so option number 2. So let lambda be an eigenvalue of t. And we have to show lambda bar is an eigenvalue of t star. So how to show this? If lambda is an eigenvalue of t, then lambda bar is an eigenvalue of t star. So if t is normal operator, then this is easy. Then you can do, but this is not saying anything about the operator. So how to prove this? Right. So first note one thing. Suppose lambda bar is an eigenvalue, then what will happen? Means what we have to show. So note let w, which is a non-zero vector, such that means w is an eigenvector of t star with corresponding eigenvalue. Let w is non-zero such that t star minus lambda bar I of w equals to 0. Means this is saying that lambda bar is an eigenvalue of t star with the corresponding eigenvector w. So this is the same thing as saying that w is in the kernel of t star minus lambda, right? Which is same as w belongs to the kernel of t star minus lambda bar I. So which is same as that kernel is non-zero because w is a non-zero vector. T star minus lambda bar I. So if kernel is non-zero, then rank will be, so then the operator is not surjective, right? So if the operator is surjective, means the kernel is 0. So this is saying that t star minus lambda bar I is not surjective. So it's saying that something is an eigenvalue, means it's saying that the corresponding t star minus lambda bar I is not surjective, right? So it is equivalent to showing this. So lambda bar is an eigenvalue of t star is equivalent to show that t star minus lambda bar I is not surjective. So we will show that this is not. So what happen if this will surjective? So if this if we got that contradiction, then we will show that lambda bar is an eigenvalue of t star. So let's assume that T star minus lambda is surjective. So let's assume T star minus lambda bar I is surjective. Right. So then let's compute this. T star minus lambda bar I W, and take this B, what is given in the question, right? So what it, this is same as T star W product B minus, so lambda bar will lambda bar W B, right? As T star, so take the other side, it will be W T V, the definition of the adjoint, and it will be lambda bar W V, and T has an eigenvalue lambda, so this is W lambda V minus lambda bar W V. So if lambda is came out, then it will be lambda bar because it is in the second variable, W V minus lambda bar W V. So this is 0, right? So this is 0 means, which implies range of, so this is true for all W, right? This is true for all W in V. So which implies the range of T star minus lambda bar I is perpendicular to the V, right? So this is in the orthogonal complement of V range, right? But we have assumed that T star minus lambda is surjective, right? So it is the meaning as range is the whole space, but as T star minus lambda bar I is surjective, which implies a range of T star minus lambda bar I is the whole space V. So V is perpendicular to the whole space, so which implies V is perpendicular to the whole space, means V should be 0. But this is a contradiction because V is a non-zero vector, which is a contradiction. As V is non-zero, right? So therefore, why we will get the contradiction? Because we have assumed T star minus lambda is surjective. So therefore, T star minus lambda bar I is not surjective, which implies lambda bar is an eigenvalue of T star. So option number 2 is correct. Now what is option number 3? If T is a normal linear operator, then lambda bar is an eigenvalue of T star. So this is trivial from the second option, right? Because this is true for in general. If this is normal, then this will be true. So let me write this. 3 holds from 2. Follows from 2. So therefore option number 3 is correct. What is option number 4? T star and T star T are self-adjoint linear operator. Let's check. t star and t star t are self-adjoint linear operator. So what you have to check, then t star, sorry, t star whole star, so it will be t star whole star and t star, and t star whole star is again t, so this is t star. So we get t star whole star equals to this, which implies t star is self-adjoint. And similarly the other, t star t is self-adjoint. This is same way you can do, right? So option number 4 is correct. Now what is option number 5? If t is self-adjoint linear operator, then lambda is real. So this we have said earlier, that self-adjoint matrix has eigenvalues are real number. So let's do this. So let t v equals to lambda v, then we have to show lambda is such that v is non-zero, because this is eigenvector, right? Lambda belongs to R, right? So then let's start with this lambda vv. So then which is lambda v times v. This you can write tv times b. Take the other way, then it will be v t star v, right? So then this will be v lambda bar tv, right? Oh sorry, t star is again t. So this will be v times lambda v. When this came out, it will came out as lambda bar vv. So what we have got, lambda minus lambda bar. So this is norm v square is 0, but v is non-zero, which implies lambda equals to lambda bar, as v is non-zero. So which implies lambda is real number. So therefore option number 5 is correct. What is the next option? If t is a self-adjoint linear operator such that t to the power n is 0, then t is 0. Right. So option number 6. So t is self-adjoint such that t to the power n is 0. We will show that this is correct, t is 0. So again we will use the spectral theorem, as t is self-adjoint which implies t is diagonalizable. Then the corresponding matrix, I am again writing it as t, diagonalizable, because there is one-to-one corresponding between the linear operator and the matrix. So which implies again there exists a O or matrix which is invertible such that t you can write O t O inverse. D, diagonal matrix. D is the diagonal matrix. With all the diagonal entries are real, right? Because this is self-adjoint. Then what will be t to the power n? It's given that t to the power n is 0, right? So then 0, this is t to the power n, and if you, so this is O D O inverse n, you will get, then this is O d to the power n O inverse, and as right, so which implies d to the power n is, sorry, let me write O tilde. This is the zero matrix, but these are not zero matrix. I am writing it O. Let it write U, otherwise it will be confusing. U D U inverse, U D U inverse, and it will be U d to the power n U inverse. Then d to the power n will be 0 because these are invertible matrix U. So, and d to the power n is diagonal matrix, and if some power are 0, then the entries should be itself 0 because these are diagonal matrix. Plus d is 0 as d is diagonal matrix. Right. So d is 0 means t is 0. Right, because t is U D inverse. So we get, if t to the power n is 0, then t should be 0 linear operator, 0 operator. So therefore option number 6 is again correct. So here all the options are correct for question number 3. Okay, question number 3 is done. Let's move to question number 4. Okay, it is saying that V be a real inner product space of R valued functions on the set S equals to 1 to n, with the inner product is defined as there, and let G belongs to V. We define the linear operator Tg on V. Tg of f evaluated at k is fk times G of n minus k plus 1. Then which of the following statements are true? First one is Tg is self-adjoint for every G belongs to V. So therefore, for that we have to compute the adjoint of Tg, right? So let's compute this. How Tg is defined? Tg f evaluated at the point k, this is fk times G of n minus k plus 1, right? Now we have to compute Tg star. So let's compute f Tg star h. So then it will be Tg f h, which is how this inner product is defined. Summation k belongs to S Tg fk times hk, right? And now use the definition Tg fk. This is k belongs to S fk times G of n minus k plus 1 hk, and this will be k belongs to S. So this you can write fk into hk G of n minus k plus 1, right? So this is same as k belongs to S fk tg of hk, right? So this is the inner product, f inner product tg of h. So if we started with f tg star h, we get tg f tg star h inner product. So therefore this is true for all fh. Therefore we get tg star equals to tg, means tg is self adjoint. For all g belongs to the head B, right? This is a function on s equals to s on the set S, which is 1 to n. So the first option is correct. It's saying that tg is diagonalizable for every g belongs to G. So this is easy because we have proved that tg is self adjoint, therefore tg is diagonalizable. So option number 2, as tg is self adjoint, so therefore tg is diagonalizable. Therefore 2 is again true. Now what is the option number 3? It is saying that if g is a constant function on S, then the rank of g is either 0 or n. So the g is a constant function, the rank of tg is either 0 or n. So this is option number 3, given that g is constant function. So let's say g is a 0 function, 0, right? Then what will happen to tg of f? Okay, it will be fk into g of n minus k plus 1, and as g is 0, so this is 0. So tg is a 0 linear operator, right? So therefore rank of tg is 0. Rank of tg is 0. Now suppose g is non-zero. So this is constant function, some constant which is non-zero, right? Constant function. Then what will happen to tg of f? K. It will be fk times g n minus k plus 1. But this is a constant, so c times fk, right? So therefore this is the identity operator, c times identity, and c is non-zero, right? So therefore rank of tg is n. The rank of, because identity operator is a rank n. So if g is a constant, then rank of tg is either 0 or n. So option number 3 is correct, right? Now what is option number 4? Saying that if gk is either 0 and 1, it means gk takes the value 0 and 1, then tg to the power m is tg. Let's check this. So gk is taking value in 0 and 1 for all k in S. So and tg, what it is, fk is fk times g of n minus k plus 1. So first let's compute what will be the tg square f, right? So it is tg of f k, right? So then by definition it will be tg of f k times g of n minus k plus 1. I use again the definition of the first one, so it will be f k g of n minus k plus 1, and again this one n minus k plus 1, right? So this is basically square f k g square function and evaluated at n minus k plus 1. So by induction you can show that this then tj to the power m f k, it will be f k g to the power m n minus k plus 1, right? But g is taking values in 0 and 1, right? So if g takes the value 0, then g to the power m will be 0, right? And if g is 1, then g to the power m will be 1, right? So therefore if g is 0, then you will get that component is 0, means it's same as at that point f k, and if g to the power m is 1, then it is same as, then g is also 1, right? And g to the power f k is also 1. So then we therefore tg to the power m will be tg, right? They will be same because you can compare with this one, because both are 0 and 1 by 1 and 2. 1 and 2 comparing. Follows from 1 and 2, right? So therefore tg to the power m is tg. So therefore option number 4 is correct. Now what is the next one? If gk is equal to k for all k belongs to S, then tg of f is the identity operator. Let's check option number 5. gk is equals to k for all k in S, then what will be tg of f? It is fk, right, into g of n minus k plus 1. And so this will be same as, because this is gk is k, so it will be n minus k plus 1 times fk, and this is not equals to fk, right? So therefore tj not equals to f, tgf, right? So therefore option number 5 is false. Because this is not true for all functions. Now what is the next option? The vector space B is isomorphic to Rn. So the vector space, what it is given, the set of all functions on S equals to 1 to n with this inner product. You have to show that this is isomorphic to Rn. Let's check. So option number 6. So what is the vector space? B is the vector space. How it is defined? So this is set of all functions. A function from S equals to 1 to n to R real valued function, right? And inner product is given, F inner product of G, K belongs to S, F K G K. So now define the canonical functions. So let's say delta nk. So let's define delta j. So how it is defined? Delta j of k. So this is 1 if j equals to k, and 0 if j not equals to k. Right? Sorry. So note that these are in V, because these are functions on from s equals to 1 to n to real valued function. So then delta j belongs to V, and you can easily show that these are bases for V. You can easily check. So these are, you can define for all j equals to 1 to n, right? So these are n number of bases. Easily check delta j for j equals to 1 to n. Forms a basis of V, right? Now we want to define a map from Rn to this. So we will map. So Rn, on Rn we have the standard basis. On Rn we have the standard basis. These are EIs, right? 0 0 0 0 1 0 0 0 0 0 and 1 in the ith place, right? So these are EIs, and we have defined. So these are for I equals to 1 to j place. These are again j equals to 1 to n. Now we want to define a map from Rn to V. Define, suppose phi we are defined from Rn to V. How it is defined? So it's enough to define on the basis. So we will define phi of Ej, we send it to delta j, right? So this sends basis to basis. So therefore, and you can check and extend it linearly, and extend it to Rn linearly. Then you can check P is linear, because that's we have we have defined it, and also because this sends basis to basis, then P is 1 1 and on 2. P is 1 1 and on 2. So therefore P is an isomorphism. Right, so we get isomorphism from Rn to V, means V is isomorphic to Rn, right? And you can also check that inner product is also preserved. So therefore V is isomorphic to Rn. So option number 6 is correct. Okay. So question number 4 is done. Let's move to the question number 5. Okay, so what it is saying, consider the matrix is given, and V1 be an eigenvector of A corresponding to the eigenvalue lambda 1. So it's saying that V1 is given and it's an eigenvector of A with the eigenvalue lambda 1. You have to find the real part of lambda 1. So let's find what will be the eigenvalue corresponding to this vector. So V1 is an eigenvalue with eigenvalue lambda, means A V1 will be lambda 1 V1, right? So let's compute what is it. 4 minus 2i 0 I 2 4i 0 I 6 Vi is 2i minus 1 plus I and 1, and so this will be lambda 1 2i minus 1 plus I and 1, right? So let's compute the left hand side. So this is the matrix multiplication. So you will get 8i plus 2i plus 2 plus 2i plus 2, which finally multiply with I will get 2, last one is 0. This will be minus 2 plus 2i plus 4i. The last one will be minus I minus 1 plus 6, right? So this is lambda 1 2i minus 1 plus I and 1. Simplify the left hand side. It will be 2 into 5i plus 1 minus 4 plus 6i means 2 into 3i minus 2, and the last one will be 5 minus I, right? So this is same as lambda 1 times 2i minus 1 plus I and 1. So the left hand side we have to write in terms of this 2i minus 1 plus I and 1, right? So 1 we have got here, 5 minus I, so the last one we can write, so this you can write 5 minus I into 1, right? So the first one we have to, so this will be basically the, because here it's 1, so 5 minus I will be the lambda 1, so this will be multiplied, then 5 minus I, then what will be remain then? If you multiply with 2i, then you will get, right, 2i. So let's check, then this will be 10i minus, so plus 2i, right? So this is correct, and again this you can write, this should be there, so minus 1 plus I and 5 minus I should be there, right? 5 minus I into minus 1 plus I, right? Because this should be the eigenvector 2i minus 1 plus I and 1, and this should be the eigenvalue. And let's check that this is true, correct or not, what we have write. So if you compute that, then you can check that this is correct. So then what will happen? So then 5 minus I will be outside, and it will be 2i minus 1 plus I 1. So this is lambda 1 2i minus 1 plus I and 1. So therefore lambda 1 is 5 minus I. Lambda 1 is 5 minus I. So real part of lambda 1 is 5. So this we have to find. So real part of lambda 1 is 5. So 5 is the answer. Okay, so question number 5 is done. Let's move to the question number 6. Okay, A star denote the conjugate transpose of A, then which of the following statements are true? So this is related to question number 5. The A is the same matrix as in 5. Here you have to check that the matrix is A is normal or not, right? So what is the matrix? A is the matrix 4 minus 2i 0 I 2, it's 2 and 4i 0 I and 6. So now you have to check that this is normal or not, means A and A star is same as A star times A or not. So let's compute A star. So 4 minus 2i 0 I 2 4i 0 I 6. A star will be 4 minus 2i 0 I 2 4i 0 I 6. Let's do the matrix multiplication. So what will get? 16 minus as minus 1 minus 4 4i minus 4i. The last one will be 2 right? It will be 4i minus 4i. This will be minus 1 plus 4 minus 16, right? Last one will be 2i plus 24i, and the last row will be 2i plus 24i minus 1 plus 36. So this is the A star, and what will be A star A? A star A, just write down. So A star, what we have? 4i 0 minus 2i 2i 0 4i 6. A is 4 minus 2i 0 I 2 4i 0 I 6. Now if you do the matrix multiplication, let's do it. It will be again 16 minus 1 minus 8i plus 2i minus 4, right? And this will be minus 8i plus 2i minus 4 plus 4 minus 1. This will be 8i plus 6i. The last row will be minus 4 8i plus 6i, and it will be minus 16 plus 36. So let's check, is this A star and A star A are 7. First entry is it's 12, here it is 15. So the first entry is itself not equal, so they are not equal. So therefore A star is not equals to A star, which implies A is not normal. So the first option is false. Is the matrix is self-adjoint? So suppose it is self-adjoint, then it is itself normal, right? Because every self-adjoint matrix is normal, but this is not normal, right? So if A is self-adjoint, then A equals to A star, right? And what will happen? A star will be A square. So this is same as A square equals to A, but this is not true, but this is a contradiction. Therefore A is not self-adjoint. Yes, every self-adjoint operator is normal, so therefore this is not self-adjoint. So the second option is again false. The matrix A is neither normal nor self-adjoint, right? So this is true because this is neither normal nor self-adjoint. So the option number 3 is true. So option number 3, this is true. By 1 and 2, right? So this is neither normal nor self-adjoint. Now the matrix A is invertible. Fourth option, it's saying that the matrix A is invertible. So let's check this. What is the matrix? A is given by 4 minus 2i 0 I 2 4i 0 I 6. From the you can see that if the all columns are, we can show that the linearly independent, then the matrix will be independently invertible, right? Because this, if it is not invertible, then some column will be written in terms of the linear combination of the other. So we will show that all the columns are linearly independent. So first column, let's call it, first column is A1, this is A2, this is A3. So A1 and A2 are linearly independent because there it has 0 and this is I. So this cannot be some lambda times some, because 0 cannot be, and this is non-zero. So note that first A1 and A2 are linearly independent, right? Because the last row here it is 0, here it is I, so they cannot be dependent. A1 and A3, so here the first is 0, here it is non-zero, and so they A1 and A3 cannot be linearly dependent by the same reason. A1 and A3 are also linearly independent. Now A2 and A3, so this has A3 as a first component 0, here it is non-zero, so they are also linearly independent. So therefore A2, A3 are linearly independent. And so note that all three together they are also linearly independent. A1, A2, A3 are linearly independent because A1 has had 0, here it is non-zero, and A3 here is 0. So they all three are linearly independent. So as all the columns are, as all three columns are Li, so therefore A is invertible. Right, because if it is not invertible, then some columns would be linear combination of the other two. So therefore the matrix is invertible. So option number 4 is correct. Now what is the last option? it is saying that the matrix A star is normal. So this is in general true, so let's check that. This does not depend on the matrix. A star is normal. A star is normal, right? So you have to solve A star whole star to show this should be the same, right? A star whole star A star. So you have to check this. So then let's check A star whole star. So this is A star. If you do the adjoint, you will get A star whole star and A star. So A star whole star is A again, and this is A star. Right, so this will get A star, and this you can write how? You can write A star whole star and A star. This is A star. So this is same as A star whole star, right? A star. So you have proved this. A star whole star is A star whole star A star. So which implies A star is normal. So therefore option number 5 is correct. Okay. So question number 6 is done, and this is the last question of this assignment. So assignment 12 is finished. Okay, and this finishes all the assignment of this course. Okay, so let's stop. So this is thank you all, and after that we'll meet in the next NPTEL. Okay, next semester. Okay, bye all. Let me stop.